What? Right. What?
Right.
Cool. Welcome. Yeah, so we're going to start. Hi everyone, thanks for coming here. For those remotely, I'm Salvador. And today I'm going to just summarize very shortly the story of our universe, which is about 14 billion years, but it will be much shorter, so don't worry, you can go back to work. And I thought on giving you an outline, but it doesn't really work because it won't be sequential and we'll be just jumping all over the place. But I thought on keeping it here just to know more or less what I'm going to talk about. So I'll give you some definitions in some points in order for you to understand later what I'm trying to say. We'll cover the expansion of the universe, why it's happening, more or less. And then I will try to give you an overview of the story of the universe from the beginning to the end, but not in this timeline, but in how people were thinking about it and then making discoveries or proposing solutions in order to build this story. And then some comments at the end. Okay, so let's start by one question. And I have to warn you, I'll probably disappoint you a few times over this talk. And I thought it was a good idea to start by a disappointment so you get into the mood. So one of the most typical questions I receive is, what is dark matter and dark energy? The sad story is that we don't know. I have no idea. But I will try to make the point on why it is important and why these two terms came out into the whole picture. But we really have no idea what they are. So that's another question today people is working on. Good. Let's start for something more familiar. This is a galaxy. Does anybody know which galaxy it is? No? Huh? It's not the Milky Way because we're inside the Milky Way, so we cannot look at it like that. It's the closest the Milky Way sister, Andromeda. Yes. Or M31 for people, for experts. It is a typical, let's say, typical spiral galaxy. It has many, many stars, dust, and gas. Gas is very important here because gas is what forms stars later, and it becomes heavier elements that form into planets and so on. By the way, this is the Milky Way. It is the same idea, but we're inside. So you have to think about this image as a panoramic view in 360, but just flat. So this end over here is connected to this end here. And we're in some point, and we can watch towards inwards, so to the center, or outwards, outside of this plane. But there are many, many kinds of galaxies, not only this kind of galaxies. And they are usually represented in a diagram like this, which is called the Hubble Galaxy Classification Scheme or diagram. It's kind of a fork, if you want. Where do you have a laser? Yes. Where over here you have what are called elliptical galaxies because of their shape. They're usually, normally, on average, bigger, redder, older. Okay? And then if you move this way, you have, on average, smaller, bluer, younger galaxies, which are spirals over here. Some of them have a bar in the center, it is maybe more clear here. Some of them don't. And then you have, so again, elliptical, kind of roundish. Spirals, kind of a disc, like Andromeda or the Milky Way. And then you have irregulars, which is just a mess. Okay? These are usually the smaller ones. Of course, it varies. The Milky Way should be around here in its classification. And then galaxies distribute in many different ways. and they form structures. So this is just a pretty picture or image of a particular point in space. Wherever you look, if you have a high enough resolution and power, you will see something similar to this. And you can see many different types. So you see the ellipticals one there, there are redder spirals there, bluish, bluer. Yeah. And then these galaxies normally organize in clusters like this, large groups. This form because they gravitationally they tend to migrate together. They feel a pull. Some of them are coming toward these nodes, and then you have filaments. I don't know if we have a clear picture here of a filament, but I wanted just to show you the cluster. But they distribute more or less like this. This is a galaxy catalog with 3D positions. This is only a slice of it. Okay? You have a map, 3 map, but you make a slice. Each point is a galaxy. And you have these nodes or clusters. Other structures that you see are filaments, which are kind of this, like they're coming toward these nodes. They connect each other. And in between those, you have huge empty regions, usually called voids. This structure is usually known as the cosmic web, because it's like a spider net or a web or something like that, just because of its shape. And these are observations. Each point is a real galaxy. So now, by the way, we're supposed to be in the center, looking upward. So now, what I want to tell you, more or less, is how we ended up in something that looks like this, in the nearby universe. Why it has that shape. So let's start by one definition, which is geometry, space-time geometry. And the usual, simpler way to say this is imagine you're a 2D or an ant or something like that. You have 2 dimensions, you're a stick man maybe, in a sheet of paper. And then you have many possibilities, but the universe has basically 3. You could be flat. This is like a sheet of paper. Or you could be, and this is infinite, it just extends everywhere. You could be in a so-called open universe which has this weird shape like what you put in a horse to ride. Okay? A saddle. Yeah. Or it could be what is called closed, which is like a sphere. The difference between those two and the sphere is that these two are the infinite, you can imagine it extending everywhere. But the sphere is finite. It has a given volume, and that's it. It doesn't have boundaries, which is something nice to have in mind. It doesn't have boundaries, but it's finite. Okay? This basically means if you start going around, then you can come back to the same point. If you do it in any of those two, you don't. You just continue. Those are infinite, the other is finite, but no boundaries. And then there are triangles here, which is the important part. If it is flat, the triangles are like in school. The angles inside add up to 180 degrees, if you remember. If not, maybe you are remembering now. And then if you're in a sphere, the angles inside the triangle add up to more than 180. And if you're in the other case, they add up to less. And this is an important point. So I'll remind you, don't worry, but keep it in mind. The triangles in different geometries have different properties. Alright, why I'm talking about geometry? Because at the beginning of the last century, this guy, who knows who this guy is?
We need to ask Cliqz.
This guy came up with, in my opinion, one of the most incredible theories that we have in physics. By the way, theory in physics or in science in general is serious. It's not like a hypothesis or a conjecture. A theory is a serious thing that can make prediction testable and has passed many tests. And you can compare to observation. It's like a real way to explain what we observe. Okay? So theory is serious. And he came up with the theory of general relativity of gravity. And this has geometry in its roots, basically. So it is a great theory. And then as soon as this theory was built, it was shortly applied to the universe, to the dynamics of the universe, how it behaves, how it moves, how it evolves. Especially by this guy. I guess nobody knows who this guy is. He's Russian, by the way. Alexander Friedman. And he basically studied, based on relativity, general relativity, how the universe should behave. And basically, it is in this form, which I will transform to this form, so it's easier to interpret. And by the way, this is the first Friedman equation. I thought it was the second, but during this talk I realized it was the first. Maybe it doesn't matter. Which basically has three terms. One that is telling the universe expands, whatever that is, whatever reason is that. The other one that it compresses, usually by gravity. So if you have mass and you let it evolve gravitationally, it will tend to pull each other together. And this side of the equation should be close to the geometry part I just explained you. Okay? So basically, it is a relation that given a certain geometry, the universe will either expand forever, contract back, or just remain equally equilibrated. There was a little detail here. And one of the implications of this, let's call it discovery, but applying these equations to the universe, is that the universe, however it is, it evolves. And he didn't like it. He wanted a static, eternal universe. And he realized that his equations mathematically allowed for an extra term, and they were equally correct, which I'll be putting in this term like this, and the ghost is a spoiler, has to be with dark energy. And then, depending on this value, you could adjust this value to get whatever the other parts are, you get a static universe. Okay? And then, well, this had to remain like that for another decade or so until this guy came out. He is Edwin Hubble. And he, in the 1930s, more or less, observed a particular tendency of galaxies to, on average, be moving away from us, and that the farther they were, so the higher the distance, the larger the distance they were, the faster they were moving away from us, on average. And this was a clear observation that the universe was expanding. Sorry for Einstein, but it wasn't static, okay? Of course, there were much debate, but I won't go into detail into this. But this is the first key observation. The other part was a theory, then this guy came out and observed this expansion from data. So this is more or less a picture. Then people started thinking, if it is expanding now, it will be bigger in the future, but also means it will be smaller. It was smaller in the past. Otherwise, you don't have expansion, right? But if you extrapolate that backwards in time, then one of the conclusions people draw was it must have been very small in the past, like very, very small. If that was the case, you have the same number of matter, galaxies, whatever you want. If that was the case, it has been denser, just because you have the same less volume, hotter, the temperature. it must be hotter in the past to cool down as it expands. If you want more details about that, we could talk later. But it was hotter and denser, okay? And this basically gave birth to the idea of the Big Bang, that the universe was in a very small, tiny, hot, dense state. And it grew to what we see today, just like that. But if that was the case, then people said, it's something telling us that the universe was hotter and denser before. And I don't remember what's the next slide, so I will just jump and then keep talking. Yes. But that idea had to wait a few other decades to came into test, where these two guys came into the story, Penzias and Wilson. They were two engineers in Bell Labs in the US, and they were testing these antennas for just communication purposes. And they had a signal, a noise they couldn't get rid of. And they tried different times during the day, they tried to identify, they account for everything they could thought about. And this noise was still there. And they pointed everywhere, and the noise was still there. By the way, this noise is, I don't know if you have turned on TV, it's not the same, but to have an idea. If you turn on TV but you have any signal and you get like all TVs, and you get like this static, that's more or less the idea. Probably that static that you're seeing is from somewhere else. We're very loud in terms of radio emission. But they account for everything and they still got some signal. And turned out that that signal was this. It was the remnant of the Big Bang people thought they should see somehow. And it was there. This is a more recent image, I think this is from the 90s, but the other one was almost nothing, so I just thought I'm showing you a better picture of it. But basically this is a map of the sky. And on average, this has 2.7 Kelvin in temperature, whatever that means. It has an average temperature everywhere. And on average, and then you see some fluctuations, colder and hotter places, which are as tiny as 10 to the minus 5, or 1 over, how much is 10 to the 5? 100,000? Yeah. 1 part in 100,000. So this is a high contrast, it's just to illustrate. But basically the story comes to the point that they were looking for something. I mean, they were not looking for this, but they ended up getting the signal people thought 20 years before they should see if the idea of the Big Bang was correct. So this is, in my opinion, one of the key observations of the whole story. This is called, by the way, I don't know if I mentioned it already, it's called the cosmic microwave background, cosmic microwave background, because it's in the microwave, is where you can see it. Or CMB, for short. And cool, so people saw, okay, the Big Bang apparently is a pretty good idea. But after all the excitement, and then analyzing the signal, then more questions came to the story. They realized that things over here and things over here were too far apart, and that in any direction, of course, were too far apart to communicate in any way. These were cosmological distances. I mean, light didn't have time to go from here to there, okay? But they still saw that everything was basically the same. And the usual analogy of this is like, if you had a cup of coffee, and you pour some milk, and you let it there, it will take time to communicate that it's now coffee with milk, and mix everything, okay? So it takes time to go from one state to the other to be the same. And if you just are pouring it and you look, you will see more coffee over here, more milk over there, and then something mixing, okay? This is basically the idea. If 2 points very far apart didn't have enough time to communicate, how it is possible that they were basically the same? And anywhere you looked, they were basically the same. This was one question. It is very unlikely that it's only by chance. That's the thing. And then the second thing, very important here, is that somehow you can use this map to measure the biggest triangles in the universe you could make. So people said, okay, let's do it, let's measure these triangles and let's add up their angles. And they turn out to be very, 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 ridiculously close to 180 degrees. So I said, okay, wait a second. And let me go back to here. We see that the universe is expanding. Okay? So this term is bigger, basically, than this term. Oh, forget about this one for a second. This term is bigger than the other one, because we see the universe is expanding. But if we measure this part, which is the geometrical part, it is flat. So this equation doesn't match. Which is, by the way, why you need this term at the end. The term that Einstein tried to put in order to have something static without moving was what it ended up solving why you see this. But I'll come back to a second. So basically, that brings us up to, again, this picture. We were seeing that the universe was like this, okay? And was expanding, that's another problem. But it was like this. Now, I would like to pay attention to this omega here. Whatever its value is, if it is bigger than 1, universe has that shape. Whatever value it has, if it is smaller than 1, it has that shape. But only one particular value, 1, out of all the reals, which are infinite if you have some math or give us this geometry. And this is the one we have. So we have two huge coincidences here. Was it God? What happened here? Are we wrong? Maybe, probably. But the thing is, you have two huge coincidences. One, the probability to have exactly that number, given all these infinite possibilities, is very low. And if I come back, the possibility of everybody being the same without having time to communicate with each other is extremely low. And then brought us to the second, in my opinion, most nice theories in this story, which was the theory of inflation, which I will represent by this. So what's inflation here? It was the idea that when the universe was very, very, very small and very, very, very young, so 10 to the minus 32 seconds old, it's infinitely faster than a blink of an eye. It's like, yeah, don't worry. It's a very small number. And if the size of a grain of sand, okay, then it was close enough to communicate with each other, okay? And then suddenly it expanded exponentially, and in a tiny fraction of a second, it expanded to many, 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 many times its size. I think it's like 10 to the 26 times its size in a fraction of a second. Which it basically means that the universe, the space-time, expanded faster than light. If you have heard that nothing can travel faster than light, that's not a problem. You cannot move through space faster than light, but space can do whatever it wants. Right? And the idea is what it expanded this fast. What does it mean? One, the problem of being everywhere more or less the same is solved because It's not that they never had time to communicate. They were together first, and then suddenly taken apart. But they already knew everything, right? And then the flatness problem is what I try to illustrate with this. It doesn't matter whatever you have as a universe geometry at the beginning. So let's imagine this is the universe sphere. And then this guy is living here. Here, this guy can see that it's curved, right? It's roundish. Maybe he doesn't see the other side, but it's roundish. It's not flat. But if it suddenly explodes, and I couldn't make it better in this animation, then it becomes kind of flat. You can imagine you're living in a yoga pole. You can see everything, and suddenly, like this, it gets of the size of the Earth. You think this is flat. People thought that Earth was flat before because they couldn't see it at scale. The point here is that inflation also solved that problem by making the universe look flat to us because it was so big, irrespective of whatever the real geometry is. Okay? So we had these two problems solved. Yes, that looks nice. But as any good theory, it also brings other predictions that then we can test. And one of them, it's maybe a little bit crazier, because it had to be with quantum mechanics. But it's basically that when the universe was this small, everything was under the influence of the quantum regime. And this crazy world, which is like subatomic scales, it's hard to imagine. Particles, you can think of photons, electrons, or other particles, create and annihilate out of nothing, and they fluctuate. And you can imagine these fluctuations like this. Okay? Like this is happening, some things pop up and then disappear, and other pop up somewhere else, and it's kind of randomly distributed. And the thing is, the other prediction of inflation is that the universe was like this before, and then suddenly it brought these tiny little tiny fluctuations to galactic scales, where quantum mechanics doesn't have to be anything anymore. Which means, and this looks pretty similar, whatever those fluctuations were in that moment, when the universe exploded in size, they remain like that. This is basically what we see now in this observation of the CMB. To put everything that I've said so far into a diagram, I like to draw the history of the universe like this. I started talking about this part at the beginning, and then I jumped here, and not sequentially, not like this, but from here to here and then back here. But this is the idea. The universe was very small at the beginning. It was weird, because quantum physics is weird. Sorry. And then, by a mechanism we don't really understand now, but we kind of accept because it solves so many problems that. Just a comment. It really, many different options, theories, or however you want to call them, have come out across time for decades. And only a handful of them could be equally good as what I'm telling you today. That's why this is the standard model. Okay? So it's really hard to make all these predictions that these crazy theories predict with other ideas. It's really hard. We have batteries, tons of observations that you need to compel with. And that's hard. Okay, coming back to this. The universe was ridiculously tiny at the beginning. it had quantum weird stuff going on, and then exploded, frozen those quantum things, whatever that means for the moment, to remain like that. And then it kept expanding at a much, much lower pace, but still expanding. In some point, the signal of the cosmic microwave background was emitted. By the way, for us, the universe is opaque to this point, so we can only test this part by predictions on this side. Okay? But this image was emitted, and this is the one you saw here. Okay? Now, what are these fluctuations? These are distribution of matter, of energy, of however you want to call it. There is a famous equation that tells you it is basically the same. So basically, what I'm just trying to say is all what I've said so far seeded or put the seeds of what we see today in the following sense. And this is a movie that I like, and I need them out here to make possible. So after all that crazy things, what happened was, basically this. I'll stop here. These fluctuations that were frozen were imprinted in the distribution of matter, which is basically gas, which is represented by this. You can see there are darker spots or underdense spots, and more brighter ones which are underdense. If that's just to its own influence, where you have more stuff, more gas, gravity is stronger. So we pull other stuff towards it. If you have less and gravity is weaker, it won't be able to fight against this stronger point, so it will lose gas. What you have at the end is that whatever is over dense, it will get denser. And as I told you at the beginning, gas creates stars. So what happened is that you were left with this distribution of gas, which had tiny inhomogeneities, but it's still enough to start collapsing and forming the first stars. And I will pause again. And those stars start grouping, creating the first galaxies, or the fossils of galaxies, which probably didn't look like what we see today, but the idea is the same. And then now I'll leave the video. And these galaxies form out of this gas, and of course gravity doesn't stop there, and they will start to clash with each other. And the regions where underdense get even less emptier, and the regions where overdense get denser and denser, hotter, crowded if you want, because these galaxies keep getting together, colliding with each other, creating even larger galaxies. And this basically creates the picture I showed you at the beginning. I hope you can kind of see it in this way. And while the video keeps running, I just want to make a comment. I haven't said much of dark energy and dark matter, which I mentioned at the beginning. If it wasn't for outside many other observations would need dark matter, in this context, if it wasn't for that, the gravitational pull wouldn't be strong enough to create what we see today. So without dark matter, we wouldn't see what we see today. We wouldn't have the Earth or the solar system. Anyway, that's the idea. But also, if we didn't have dark energy, and it wasn't expanding everything, the collapse would have been stronger, so probably we wouldn't have the Earth and the solar system either. Apart from other observations that require this component. But at the end, in some sense, you wouldn't be here if it wasn't for dark energy and dark matter, even when we don't know what the hell they are. And now the video is finishing. So basically, this is a simulation that's trying to reproduce more or less what we see in observations. And you can see again filaments, clusters, empty regions, and then galaxies that kind of live around there, but most of them are here. Which brings me back again to this. That video and what I just said is about 90-something% of the story of the universe. So all my talk was about 380,000 years up to here. 380,000 years ago, humans were already wearing clothes and cooking. Clothes. Okay. And then everything else is just much more smoother, but in my opinion, equally interesting. How very crazy stuff happened there, and then you just let it there by its own, and it starts evolving, creating what we see today. Right? I'm kind of finishing. Just another comment. I don't know if you can see it here, but this is supposed to represent expansion. It's very steady here. It is crazy here, of course. But now it starts to open up again. This is what we measure. And that is what we think is caused by dark energy. If this keeps happening, what is the future? Well, the future is everything will keep moving away from each other, as Hubble's observation showed in the 1930s. Faster and faster, it accelerates. Everything that is already very close or bounded will remain bounded. So clusters will stay there, maybe they will get new members, but among them, it will start expanding and going farther away and faster and faster and faster, up to a point where you won't be able to see it. And then these guys start basically getting old, stars die, and you get others, but they eventually die, and at a certain point, every star dies, and the universe is dark. That's it. Right? This will take millions of years, so don't worry. But if all what I told you today happens to be what happened to be true, it's a very sad end. That was it. But so basically, enjoy what we can see now, and it won't change over your lifetime or your grandson. So don't worry. Which brings me to the last video. What I'm going to show you now is the end of my talk. I hope it wasn't too confusing. This is a video made by the people involved. Not only them, they made the actual video, but there is more people involved in this project, this Long Digital Sky Survey. I based my PhD thesis in that data, so for me it's very familiar. Not this one in particular. And what I'm showing you here is a flight through our real local universe, our neighbor. Each position of this galaxy is a real position. In its image, almost all of them are how those galaxies look like in reality from our telescopes. The only thing that is not real is the size. The size has been boosted, I think, like 10 times. Otherwise, because they're so far apart that if you make it a scale, you just see dots. But basically, you can really think of this as if you were flying through our neighborhood galaxies. And then most of them are bigger than ours. And if you then think about how tiny the sun is compared to our galaxy, and how tiny the Earth is compared to the sun, and how tiny you are compared to the Earth, and you look at this, I'll leave it there. Thank you. Those are the credits, by the way. Many universities. I don't know if we have time for, Mara, do we have time for questions?
Yes.
Okay.
Many minutes.
Okay. I know I have a question from Gabor, especially, that I didn't talk about. I think about the holographic principle and all these alternative facts or news that were around in my opinion. I guess first we could have a question about this, and if many people are interested, or we just have time, then we could. I mean, it won't be super short because I have no idea. So questions.
Well, I have one. You told that the stars are dying, but they have some energy, yeah? What happens with their energy? So as we know, the energy gets transformed into some other form. It doesn't disappear.
Usually, when stars die, they really explode, like a supernova, or they explode, which is not as violent as that. But basically, you are propelling their material outwards.
So it's another new Big Bang, or it's another?
No. It's a supernova, for example, or a tiny explosion of one star. Okay, which means basically the energy you said is transformed. Well, the energy that these stars have is transformed to kinetic energy movement of this material. This material was at one point there, and then you kick it out. So that's your transfer of energy. More questions?
Mine is really quick. Does this knowledge make you more humble in your day-to-day life?
Only when you Yeah. Actually, it's nice to give this kind of stuff because when you work in this, you lose the whole picture. I mean, you code all day, then you can put some numbers, then you write some text, and you are very specific in a tiny fraction of a measurement that you lose the picture. So yeah, when I remember what it's everything about, which is once in a while, yes.
You kept on repeating how tiny the universe was just before the Big Bang. Are there any guesses or any comparison just how tiny it was? Or is it just saying it?
So I would say the problem is with the Big Bang is that we put a name to something which basically starts behaving as we can explain it with our knowledge of physics. The problem going backwards is that at that point, the physics just break. You can't keep going backwards. It's like dividing by zero or something like that. Okay? Which, by the way, I didn't mention. At the Big Bang there was no explosion, by the way. It was just zero. That's it. It didn't no. It was the tiniest point that we can explain, and then it grew. But yes, we can't say anything before because we have no means to go beyond that. With this theory, there are all the theories that solve that problem somehow, but they still need to pass all the tests. This one has passed, basically. You.
If the universe is expanding at the rate, if the universe expands at a certain rate, it would mean that we won't be able to see any night sky, right? The stars at some point. Always.
Yes, very far in the future we won't see.
Expanded faster than
We
light.
still see. No. The sky we can see like every day without any telescope will still be there until those stars dies because those are part of the Milky Way.
So we'll see the past. Not beyond the Milky Way. So everything that's been
Yes, exactly.
expanding.
So in some points of the galaxies that are outside our group won't be visible in theory, yes.
So at that point, we want, if let's say that everything dies, all the research dies, they will have no idea as to how the universe could be explained because there won't be such thing as a universe. It's just darkness.
Exactly.
Well, then, isn't any alternative theory which takes into consideration what Friedman suggests about contracting and expanding universe, where what we've noticed projects itself into a point with a infinite volume and density?
Could you repeat the last part?
Okay. So technically, is it possible that the model that we've chosen to make sense of the expansion of the universe, the Big Bang, which makes us project the universe into a point of zero volume and infinite density, is in fact better explained by a theory that takes into consideration what Friedman suggests with regard to an expanding universe. And what we've happened to notice now, and to take observation from, is just the expansion part, and which makes us suggest that everything leads to a point. Is there any such viable theory that suggests such thing or studies it?
You mean towards the future?
No, in general, to make sense of the universe in a, let's say, Kondratian.
In some like bouncy way.
Yeah.
Yeah, so all the observations we have so far, which go as far as 90-something% of the story of the universe as we understand it, the universe was always expanding. Okay? So either it was contracting before the Big Bang, which we cannot test because our theories don't work. It was always expanding. So at the end, you don't have a compelling reason to think it will crash in the future. And then you have the the problem that is the future. So you can make conjectures. What I just said about the future is just a hypothesis, but we have no means to test it. Although the theory that works with everything that we can see in the past predicts that. There is no room to accommodate something else unless you put something really that you put by hand.
There is one theory which says it that when it expands, it becomes so much so sparse that there is no time and energy as it is. You can think of it as like this small again.
Yeah, I don't know if I
don't
would.
remember all this.
I don't know if I would put it theory for
Not
because
theory,
but there are many of these ideas, and then it becomes a philosophical discussion. But from this more scientific point of view, you need to take these ideas, make some predictions, and compare them to observations. If you can't do that, then it's nothing else than just another idea of how it could be. And for imagination, we could think about infinite stuff.
So you said that the universe is expanding. So while the universe expands, what is it filled up with? Is it filled up with dark matter, or is it like an empty space?
That's the dark energy problem, basically. Dark energy is dark because we have no idea what it is. And energy just because in the equations we represent everything as energy, and it's a component that we don't know what it is, but it's necessary to fit observations. Okay, and it seems to be in density. So if you imagine as energy density, so amount of energy per unit volume, it's constant. It's like it is big. The universe gets bigger, but then the dark energy is the same, so it's kind of creating all the time. That's one of the most fundamental questions that are open today. What is that? One option is that the vacuum doesn't have zero energy, but it has some energy. And if you create more vacuum, you create more energy. But that's just an idea that has some mathematical background, but still an idea that needs to be tested.
How do you know how much universe is still there? Because it's expanding faster than don't do secret.
Mhm.
There is a horizon which.
Yeah, so everything, in general, when we talk about the universe, we're talking about the observable universe. We have no idea what's happening beyond what we can observe. So, and that's so impossible to answer that we don't even make questions about that. There are some ideas about like universe as bubbles, and that there are other bubbles outside our observable universe. That for some reason they seem to be reasonable to think about that, but then you cannot again make any prediction, at least for the moment, about something that we could observe that could prove that. So everything is our observable universe. Okay?
But I'm asking because if you don't know how much is it, how do you know about what the size was of the small? When it was small.
Exactly. That's a very hard to answer question. I should say a good question, but it's hard to answer question. But that's the thing. That's another quality of the Big Bang theory. The idea of telling it was very small is just to make an analogy to understand. What we see today was that small, but if there is more over there, it only means it was hotter and denser before, and the distances we see today were much closer before. It comes back to the idea of infinite, but maybe finite but boundless geometries. For example, the grain of sand is what we can see today, but if there were more outside, it was bigger.
But basically, this cosmic microwave background is the horizon, right? That we see.
But for different reasons.
Gauges.
For different reasons. We base everything in light, photons, or electromagnetic signal, to be more precise. And the universe beyond that point was opaque. If you want a bit more details, photons were coupled to matter, so they couldn't travel. They were just there, trapped, let's say. We could look further if someday we master something that is called like neutrino telescopes. Neutrinos are other kind of particles. I think last year the people who discovered the mass gained the Nobel Prize, if you ever saw that. Anyway, neutrinos are supposed to decouple before photons from these mixtures of anything. If we were able to be as efficient detecting them as we are with light, we could see a bit further. But that's a different boundary. It's just a matter of how we see things compared to what is our...
But that's kind of the thing that the furthest away that we can see right now.
That's what I'm trying to say. We can see using light further than the CMB. But there is another limit, which is where the expansion is faster than the speed of light. So the light that is emitted over there never reaches.
Right. But when you talk about the observable universe, this 14 billion years or whatever it is in size, that's the boundary.
It's the second.
Sorry?
It's the second. The second one.
Okay.
Yeah. There is a portion of the observable universe that we can't really observe in terms of light, but we still can test in terms of its consequences to what we see today. Any more questions? I don't know. Do we have more time?
Or one more.
One more? Or not?
I have one before the last one. In our lifetime, is it likely to expect that we will get more insights? Or because looking in the past, the increasing knowledge actually increased very slowly, very increment over decades usually.
Yes.
So now with new technologies and everything, is that speed of knowledge acquisition going faster, or
So yes, so 20 years ago we were able to observe basically a couple of galaxies per day, for example, per night to be more precise. There are now building experiments that will have of the order of petabytes of information per hour. So one of the challenges actually for that is to cope with that in terms of technical terms. Software engineers, and storage, and all that. So you could imagine the precision of the measurements and whatever comes directly from there will increase exponentially. What I told you today, now we have for some measurements 1% accuracy of that, and 20 years ago they were, I don't know, like 80% error bars or something like that. So in that sense, yes. From other point of view, in terms of ideas of how to solve the fundamental questions we still have, that's something we cannot tell, right? We basically need I don't know, Einstein or something like that, just to come up with a completely new, different idea that solves everything. Or some other clever ideas like inflation that solve some of the problems and make us progress. So I expect that yes, I don't know if it's super fast, but the first part of the story were like 60 years, and then the second part of the story were like 20. So it was faster. At least in this sense it was. And now we're in a point that where people is more focused on precision, so getting things right instead of moving faster. So rather, let's do this right. Yeah. I hope so, anyway. Okay, we're done. Thank you. Bye.